All right, hi everyone. Welcome back from Thanksgiving break. Hopefully everyone had a great break. So today we're going to focus all on DNS rebinding. So the whole class is just going to be about that attack that I left you hanging with before break, if you remember. But before we start, just some admin stuff. So there's going to be no more assignments in the class. So the last assignment isn't going to be a thing. So it's sort of hard to pull it together. The assignment didn't really come together in the end. So hopefully you just enjoyed the extra time for preparing for your other classes and studying for the final in this class. I'm going to release a sample final this Friday, so you can see what the final exam is going to look like. It's going to be a written exam. And it's going to be kind of similar to assignment 2, so just sort of questions, like you saw in assignment 2, and I'll give you a sample exam so you can get an idea of what it'll be like. Also, course feedback is open on Access now, so feel free to submit feedback about the course. It's completely anonymous, so I can't see what anybody says, or I can't see who said what, but I obviously can see the feedback. And it's incredibly helpful because this is a brand new class. So I really want to know what you truly think about both just the format of the class, the way that I've been lecturing, the content of the class, just anything like that. Even just like order of topics, just whatever you feel like would be extremely valuable to me. I really would appreciate that. Cool. Any questions before we start? Cool. All right. So let's do it. So so there's a bunch of stories about DNS rebinding in the news. This is one. So this is one of the earliest articles about DNS rebinding. It was an attack that was discovered by this guy named Dan Kaminsky. He presented it at I think it was Black Hat, maybe it was DEF CON. It was really an underappreciated attack when it was first discovered. I mean, you can see that by this headline, it's pretty dramatic headline, but despite the fact that it seems like such an extreme when it was first presented, it seemed like such an extreme attack. People sort of ignored it for like the next 10 years, and so it's still actually a pervasive issue even today. Even though you can see that it's, this is from 2008. There's a more recent article. There were vulnerabilities discovered in pretty much every single IoT device that were related to DNS rebinding. So some of the vendors are Google, Roku, Sonos. Basically, any device that like connects to the Wi-Fi hotspot in your house was vulnerable to DNS rebinding. And so, that's what I mean when I say that it was really underappreciated when it first came out. And even today, like, it's actually really hard to describe. That's why I'm like devoting this entire lecture to trying to explain it. I've tried to explain it in the past to other people and struggled and gotten all mixed up while explaining it. It's sort of subtle and tricky. Also, fun fact, in some of the open source code that I've written, I actually wrote a DNS rebinding bug, and my own code was vulnerable to it. And then when somebody pointed this out and I added a fix for it, it turned out that for like the next 6 months, that fix actually wasn't doing anything, even though everybody who tested it thought that it would actually solve the issue. It was still vulnerable to DNS rebinding for the next many months. So yeah, it's a really kind of tricky issue. But yeah, so yeah, like I said, pretty much every IoT device is currently or was vulnerable to this. Every local server, either is or was vulnerable to this. When I say was, basically when it's not too hard to fix. But if you're not aware that this is even a thing, then you're probably vulnerable to it. Is the lesson here? Yeah. So here's some stats just from some security researchers, just to get an idea of the scope of this. 66% of printers are vulnerable to it. 75% of IP cameras, so those are like internet-connected cameras, that let you see your house when you're on the go from your mobile phone or whatever. 77% of phones, 57% of smart TVs, 87% of switches, routers, and access points. This is a really bad one because if your router is vulnerable to this, it means that an attacker can basically get onto the router and change the settings of your router. They can maybe set up a proxy, intercept all the traffic going through your router. So it's really bad. And routers have some of the buggiest and crappiest software on them for whatever reason. And so yeah, they're the highest number that were vulnerable to this. And then 78% of streaming media players and smart speakers by Apple, Google, Roku, and Sonos. So yeah, very stunning numbers here. Yeah, so this is one such device. I just picked a random device. But this one was pointed out by, there was actually a recent, like I think it was a year ago, somebody just sort of was like, hey, everybody, remember DNS rebinding, that thing that was discovered like 10 years ago? I'm going to go and look at all the devices that are on the market today that are IoT devices and see, which ones of them now are vulnerable to this. And this thermostat was one of the ones that was vulnerable. And so basically what could happen is you could be browsing the web in your web browser, and you go to an attacker website, or an attacker buys an ad. The ad loads in your browser. It's a very easy thing to do, right? And that code, the JavaScript code, makes a request to your thermostat, which has a server in it, and is listening on your local network. So it's just like your laptop is connected to the network, the thermostat is connected to the network. And so this ad makes a request to the thermostat using the thermostat's IP address. This request is completely unauthenticated, and it was literally just a GET request. So you could send a GET request and change the temperature. And it went up to like 95 degrees, so you could sort of change the temperature in the person's house up to 95 degrees, which maybe not such a bad thing, but there's some things I hadn't thought about, like so the person who discovered this was writing about potential things that you could do with this. It could be dangerous or deadly in the summer months, in certain climates, and if you have an elderly or disabled occupant, you can imagine it being really deadly. Also, yeah, if you're targeted while you're on vacation, then your bill will be really large when you come back, and so on and so forth. And of course, it's also possible for a device to be like, not just a request could not just be able to change the temperature of the thermostat, but perhaps it might actually run the code that you include in the request if the server is just that buggy, right? Yeah, so that's not good. So if you remember, we talked about the way that the Zoom server was vulnerable to basically websites could cause the Zoom program installed on your computer to join you into a Zoom call without any interaction. And so we went through a sort of series of steps, if you remember last time, and we got to a point where it seemed like we should be able to, by making a certain set of changes, make this Zoom server secure. And then I told you at the very end, like, actually no DNS rebinding. But let's review what we went through last time, and then we'll see sort of how to take the next step to make sure that it's secure against DNS rebinding. But I just want to make sure everyone's on the same page, because Thanksgiving break was a week long, and you probably all forgot. So if you remember, we have this server running locally on our laptop because we installed this Zoom video conferencing software on our computer, right? And it's listening for connections on that port right there, 19421. And here's our browser, and we visit the Zoom server. We go to some URL, and the server returns us a page. Once the page is loaded, that page fires off a GET request using the fetch API to this URL, and in particular, it's directed to the local server on our computer. And the local server just responds by launching the Zoom app, and then it returns a response here back to the page, and then the browser says, yeah, that's fine. You can read that because this request was initiated by Zoom, and this header here says that Zoom is allowed to read the response. So even though this is a cross-domain request because it's a request from Zoom to a completely different origin, we're going to be able to read the response because of this header. OK. Right. OK. So does this make sense, everybody? Should all be a review? OK, cool. So now we said, obviously, that the problem with this is an attacker can join you into a call. How does the attacker do that? Well, the attacker sort of follows a similar set of steps as the legitimate case. So the attacker gets you to go to their page. The page loads. They fire off a request to the server. The server launches the Zoom app. The server, everything is exactly the same up until this point. The only difference is that this time, because the request was initiated by attacker.com, and this header is saying that only zoom.us can read the response, the browser is not going to let us read this little result success JSON response. But who cares? We were able to launch the app, and we were able to join the user into our chat room and turn on their camera. So really bad. Right. So this. Again, this is review. OK, so let's fix the issue. So I mentioned that probably the best solution would be if Zoom didn't have a local HTTP server at all, because there's a way to register what's called a protocol handler, and native apps can do this. It's basically a way that a native app can say, hey, I'm going to invent this new protocol called, let's say, Zoom://, And anytime somebody goes to one of these URLs, please launch the app. And so an application installed on your computer can ask the OS to do this. It can say to your OS, this app is capable of handling these types of URLs. And so if they did that, then all they would need to do to sort of get this user experience where the user can click a link and end up in a call is they would just redirect you to this Zoom URL. And then your browser would say, hey, I don't know what to do with this URL. The browser only handles HTTP. So the browser would say, hey, I can open up this app for you that this app says it can handle this protocol. Would you like me to open this app for you? And if the user says yes, then bam, they're in the app. So that's probably the safest, most straightforward way that they could have solved this. But let's assume that for some reason, this approach wasn't acceptable to them, and let's say that you really want to do a local HTTP server, even though it's probably a bad idea. How can you do this securely? The reason why I say that it's probably a bad idea is just because there's all these things you have to worry about. But there are some cases where it's legitimate. There's some cases where you want to do this. So I'll mention a few in a bit. I think at the end I mentioned a few cases. Yeah, so say they wanted to keep the local server. So one idea is they could require user interaction before joining the user into a call. So say that they didn't solve this problem here. They let the attacker cause this request to go through to the server. What if the app were to just pop up a little dialog here and say, hey, you're about to join a call. Do you want to join a call? That's an acceptable solution. It's still a bit strange that this server is letting requests come in from random origins, but they would have solved this issue. So another idea is if we could find some way to ensure that only Zoom.us, which is their origin, is able to communicate with the local server, then we don't have a problem anymore either. So last time we talked about how to do this, I mentioned this concept of simple HTTP requests and pre-flight HTTP requests. There's two types. So if you remember simple ones, the easiest way to remember it, there's like a bunch of things up here, but the easiest sort of heuristic to keep in your mind of how to distinguish these two. Does anybody remember from last time? I said there was like a really easy way to remember whether a request is simple or if it's a pre-flight. Anyone remember? It's OK. Thanksgiving was a long time, so OK, I'll just tell you. So basically, any request that you could create with just HTML is a simple request. So pretend you can't write JavaScript. You're not allowed to write JavaScript. You can just write HTML. Yeah, let's forget about CSS for a second. Just with HTML, what kinds of requests can you cause the browser to make? So obviously, you can cause GET requests, right? You can include an image tag. And the browser is going to see that and make a GET request to that URL. And so that's why you see GET up here. Post is also possible with a form, right? So an HTML form, when the submit button is clicked, will cause a post request to get sent. But when it does do post, the form is actually only able to cause posts that have one of these three content types. And this is sort of configurable in the form, in the HTML of the form. So if the content type is not one of these three, then it's not a simple request, because it wouldn't be possible to create such a request with pure HTML. And lastly, obviously, with these types of requests, there's no JavaScript code, so we're not able to sort of configure the HTTP headers or like add custom HTTP headers to the request. There's just going to be some default headers that the browser attaches to these requests. OK, so this is what we call simple requests. And then pre-flighted requests are basically anything that goes beyond that. So say that we go ahead and write some JavaScript and we say, oh, we want to add this extra header to the request. Well, then it's going to be a pre-flighted request. Same thing with if I wanted to say, for example, send a put or a delete as my HTTP method. These are not methods that are listed here in the simple case, so that's going to be a pre-flighted request. OK, so whenever we attempt to do a pre-flighted request, the browser is going to check to see that it's safe to do that, because it doesn't know in advance that the server is expecting such requests to be able to happen. And so the way that it checks is it sends another type of request called options to the server. And that's basically a request to be able to send another request later. And in that options, the browser is going to include all the relevant information, like basically the details that make this request not a simple request. OK, so say for example, the request is a put. It's not a post, it's not a get, it's a put. So the browser will say in that request, hey, am I allowed to do puts? And by the way, this is the origin that's asking. And depending on how the server responds, this will either be allowed or denied, right? So and then of course we have to think about the case of what happens for all the servers that were on the internet before this standard was created, because this is a relatively recent standard. There's all these servers that were written in the 90s that are still on the internet. How are they going to respond when somebody shows up and starts sending them options requests? Well, if they don't support options, then they're going to respond with some response that presumably won't include the exact headers that we need to sort of tell the browser, hey, this is OK. And so the browser will interpret anything that doesn't explicitly say, this is allowed as this is not allowed. And so it will basically deny. The default here is deny. So that's the idea of preflighted requests. Yeah, I guess the other thing I would add is just that this kind of, if this seems arbitrary to you, it is kind of arbitrary. Like this is the fact that we chose these methods and the fact that this is really arbitrary. This is like a lot of the things in the web and the way the web is designed. It's sort of a very pragmatic decision. The reason why these things were chosen is because basically for a long time, people had to assume, basically from the beginning of the web, people had to assume that a web page can send these kinds of requests, right? And then later on, when new types of things could be sent using JavaScript, servers that had made assumptions might be surprised by the new types of requests that can come to them, right? Things that they thought couldn't be generated from page. And so rather than just letting those servers get owned, we sort of said, OK, we should introduce this new method where we sort of ask for permission before going and doing this without, we should ask permission before we do this thing that the server might not be expecting is possible. OK, so we went ahead and said, OK, so let's solve the problem of our server getting these random requests. If you remember here, it was a get that was causing the app to launch. And so what if we say, hey, let's make this not a simple request, because this currently is a simple request. That means any page can send these requests without a preflight happening, without that options request going out first to ask the server for permission, right? And so maybe if we change the method, so we say that we get rid of this get here, we make this local server expect only put, and it won't do anything if it gets a get. Maybe we can solve this problem. And so last time we went through that, and what we saw was, so yeah, the flow is all the same up here at the beginning. We get this page from the server, and then once the zoom.us page has loaded, we call fetch. But this time we specify put as our method. And so now the browser is going to say, hey, wait a minute, this is not a simple request. This is a preflighted request, so I need to check first with the server to see if it's OK. And so how does it do that? Well, and I'm representing the browser, the browser here as sort of this like middleman, like not letting the request go through until it's asked the server if it's OK. So it's going to say, so yeah, this is not same origin, and also this is not a simple request. And so therefore I need to check first. So the way that it checks is it sends an options request. And it includes, in particular, the method it would like permission to use. And it also tells the server, hey, by the way, this is JavaScript code that's running on zoom.us. So maybe that factors into the decision that the server is going to make. And so the server, in this case, we would be very concerned with what the origin is here. And we would say if it's Zoom, then we'll go ahead and allow it. And so we indicate that by responding with an empty response, but the important point is that we included this header here that tells the browser that it's OK to do puts. And so then the browser says, OK, looks like it's fine. And so now that request up here that was initially sort of held in limbo is now allowed to go through. And then now the server just goes ahead and sort of blindly launches the Zoom app because it knows it's relying on the fact that the browser wouldn't allow a put to go through unless this process had happened before. So we're leaning on the browser to do that. And then the rest is the same here. OK, so does that make sense? So far, it's still pretty much all review. Yeah.
Is there always a request? Can that like cast and stuff like
That can get cached. So yeah, that's a great question because you can imagine this adds like a ton of overhead to every single request. So yeah, there's a way to indicate in the response how long to cache that for, and then the browser will just like it will skip the options requests in the future. Cool. Any other questions? Okay, so it seemed like we solved the problem here, right? Because I don't know if I have the slides. Yeah, here. So yeah, I have the slides here. So this is like if an attacker tries to now attack our server, what's going to happen is, well, the code that the attacker is running generates this put, and then the browser, it's going to notice, okay, this is a non-simple request. And also, the bigger problem is that it's not same origin, it's not a simple request. So we have to go ahead and pre-flight it, and so we go ahead and send that pre-flight request. And this time you'll see the origin is set to attacker. So the server is going to say this is not zoom.us, so no, you're not allowed. And it'll send back, basically anything it sends back that doesn't include allow will be treated as a deny. In this case, I'm just using the HTTP code 403 because that's actually a code that specifically means you are forbidden. It's just kind of like nice documentation to include that method, but it doesn't, or that response, but it doesn't actually matter. And then the browser will deny the request. And so that request that was held in limbo won't actually be allowed to go through. Does that make sense? Should, right? OK, cool. Great. So basically, it seems like we solved the problem. But yeah, we'll see why it's actually not quite solved in a second. But first, we should also remember that there's still certain cases where the app can be launched by others. By others besides the zoom.us server. So one example is that a native app running on the same device can send a put request, and it doesn't have to follow all these rules that the browser is enforcing, right? So we're relying on the browser to say, hey, if there's some JavaScript code running on attacker.com, don't let it send a put request unless you've done options first. But if you have an app just like running on your computer, like a Python script or something, or another piece of software that you've installed, it can go ahead and create HTTP requests to wherever it wants. It doesn't have to follow these rules. This is like the browser just has code to follow these rules. But of course, a script that you write doesn't have to do this. A script that is some code that's already running on your computer might not be following these same rules. And so it's just important to remember that, like, yeah, we don't have to. This options process is totally enforced purely by the browser. Does that make sense? OK, cool. Yeah. So let's see here. Anything else I want to mention? Pre-flight requests allow the local server to prevent. Yeah, exactly. That's the main point. Is just keep in mind, this is a thing the browser is doing for us. OK, so yeah, the DNS rebinding attack. So all of the work we put in to make this local server secure, it still hasn't amounted to anything because you can still send a request through from any origin on the web. And the way that you do that is a DNS rebinding attack. So the idea with this is you can basically trick the browser into thinking that the request that's being sent doesn't need to be pre-flighted. So you can make the browser think that this request to the local server is actually a request from the attacker to the attacker. The browser will see a request from attacker.com going to attacker.com, and it's going to say, hey, this is actually a same origin request. So it doesn't matter how complicated, it doesn't matter if it's a put. It doesn't matter if there's custom headers. It doesn't matter how customized the request is. It can be any request because it's from the same origin to the same origin. So it's going to be allowed by the browser. And that's the key. That's sort of why the attack works, is a way to trick the browser into thinking that this request is not actually cross-origin request. OK, so let's talk about like how it actually works. So well, I guess first some of the capabilities of it. So it allows the attacker to basically bypass the cross-origin rules. And also another thing you can do with it is you can bypass the victim's firewall. So you can basically use their browser as a proxy to communicate directly with vulnerable servers that are on the same network as them. So this is sort of beyond just attacking local servers on your computer. You can actually use this approach to attack vulnerable IoT devices that are on the same network as you. And one thing to keep in mind about how this works is that so the same origin policy is actually not being violated here. So this is, remember the same origin policy we talked about it. It's one origin can only talk to the other origin, and the origins are defined as protocol plus hostname plus port, right? And so this is actually being followed perfectly, exactly. The attack doesn't involve a violation of the same origin policy. The problem here is that the same origin policy doesn't actually care about the IP address of the server in question. That's not part of what defines an origin, right? So we'll get into exactly what this means in a second. But that's that's something to keep in mind. That's going to be the crux of this attack. So let's see here. Yeah, I have a demo of it. So we're going to actually see it in action. And hopefully that makes it a little bit clearer. OK, so I have some code here. Can everybody see this? OK, nice. OK, so we have two servers. And if you remember from last time, the server on the left here is this is the one from before. So I remember I wrote a sort of a vulnerable server where if you send it a request, then it will open up the dictionary on my computer. And we showed that any site that wanted to could send a GET request to this server, and this server is running on port 8080. And so anybody can literally just make an image tag and point it to 8080, and then this will cause the dictionary to open. And we can actually just see that in action. So the server's already running. So if I literally just visit, if I go here and I refresh this page, you'll see that the dictionary is opened, just like that. And actually, I noticed later when I was looking at this, that they have this, Wikipedia has this image here where they claim that the popular culture image of a hacker operating in a darkened room is rarely accurate. I don't know if that's actually true. It seems it's pretty accurate a lot of the time. But anyway, OK, so, and then I also showed last time that if you go to a site like example, and then you do something like, you make an image that points to localhost 8080, and you just create this image in the context of example.com. Well, you can see there that that site is able to pop open the dictionary on my computer because again, this server is just going to accept GET requests from anywhere, and the browser is not going to stop it because it's a simple request. Did everybody follow this? Right. So this is a simple request. OK, so what I wanted to show a few things. So let's see here. So yeah, we can actually just do that right here in line. So what I have here is another server, and this is going to represent the attacker's website. And what I want to show here is that the attacker can just write some code that's going to trigger this server. And I guess I kind of already showed it, but I'll just write it here to be absolutely clear. So I can basically add an image to this page and make it send a request to localhost 8080. And just like that, if I visit that now here in my browser, what I actually should do is make this attacker.com 8080. That's what I meant. Yeah. OK. Yeah. So just like that, we actually have the same thing happening. And if I open up the inspector here, what we see is that I'm on attacker.com, and when I load this up, attacker.com is actually making. Wait, where's the request it's making? It's supposed to be making a request to the local server, but I don't see it here. Interesting. How is the dictionary opening then? OK, if I refresh, that's weird. Oh, I'm visiting 8080. Sorry, I'm on the wrong port. Yeah, thank you. Yeah, OK, sorry. Yeah, so it's because it's an alias. OK, there we go. That's what I wanted. OK, gotcha. OK, so I'm on attacker.com, port 999. And if you look at the HTML here, it's literally just including an image that's pointing to this local server on my computer. And so when the browser makes that GET request, it causes you can see the request being made right here, localhost. It's going to localhost, and you'll notice the response is like some garbage that's actually not a valid image, and that's why you see a broken image there. But the dictionary still opens. OK, so what I want to show now is if I change this to use fetch, we can get a little bit more detail about the request. So if I change this to fetch localhost 8080, and then I get the response, and I turn it into text, and then I take the text and I turn it into, let's see here, I will take the text, and what do I want to do with it? I will do document.body.inner HTML plus equals, how about I just add the text to the page? This is extremely unsafe because this could contain HTML, and we'd have a cross-site scripting attack, but that's another issue. It's OK for now. And then if there was an error, I'm going to catch the error, and I will add the error to the page in a similar fashion so we can see what the error is. And I think one other thing I want to do here is I want to add a line break just so that I can see this a little bit easier, like that. OK. OK, all right. I think that's right. OK, so now all I'm showing here is that now if I refresh with the inspector open, I should see. Let's see what happens here. Huh.
I think you didn't close the script tag.
I didn't close the script tag. Oh, thank you. Thank you. Thanks to those of you who are paying attention. OK. Yes. Perfect. OK, great. So yeah, so you can see what happened here is, again, it worked. And the main difference here is that now the response that the server sent back, which is success, we're able to take that and include it in the page. And the reason why we're able to do that is because on the request itself, when you look at the headers, you'll notice that the server, for whatever reason, this local server decided to send in the response. Let's see, where is it? No, it's I need to click the localhost one. Yeah, this is the request I want. Yes. So we tried to load localhost, and the response contains this header here, access control allow origin, which is set to star. And what this means is that any page is allowed to read the response out. And so that's why I was able to take this text success, read it out of the response, and include it in the page, even though I'm an attacker, right? OK, so we can fix that problem pretty easily. If we just go here to our local server and we delete the access control allow origin star header that we're setting, then we can go ahead and now prevent the attacker from reading the response out. So now if I refresh, we'll see is that, again, the dictionary is still opened, but what you'll notice is that this time the response is sort of opaque. The page can't see it. It's blocked here. And you look at the headers, and you'll notice that that header is not being set. And so as far as the JavaScript running in the page is concerned, it's not allowed to see the contents of the request. And so it gets this error saying that it failed to fetch. But the truth is that the GET request actually got sent to the server, right? Because the way, if you remember, the way that this enforcement happens with this header is the request goes out, it comes back, and then the browser looks at whether this page is allowed to read the response. OK? So because this request is not a pre-flighted request, the browser doesn't need to check first before it sends it. It just sends it, it goes through, the response comes back, and then it decides whether it's going to let this page see it or not. That's distinct from a pre-flighted request where it actually asks for permission before it even makes the request, right? So just keep those two cases in mind. Does that make sense to everybody? OK, cool. And then what I want to show now is, let's see here. Yeah, so I had one other thing I wanted to show. Need to pull up. You know what? Actually, I'll just pull it up here. OK, I think that was actually it. So for now, and I have another thing in a second. So yeah, we showed basically. So basically, we showed how to use the browser to make requests to local servers, and we sort of use the browser as a proxy. Like this attacker code is running on our browser, and it's talking to this local server. And we saw how we could remove the access control allow origin header, but that actually doesn't stop the attacker from sending the request. It just stops them from reading the response. Sorry. The last thing I wanted to show was what we actually talked about as our defense, right? So we mentioned that a way that we thought we could change our server to prevent this is by changing it from a GET request to a PUT request. So if you see here this one word GET here, I'm just going to swap it out with PUT, and then now the attacker has to send a PUT request. And so if they try to do that by adding a little option here, method PUT. So right here, does everybody see this? I just add a little extra parameter to the fetch call, and now it's going to attempt to make the method a put. And so now the attacker's like, okay, I guess this is going to work, right? But when we refresh, we see that this time it still says failed to fetch, but it's even worse than before. Before, we couldn't read the actual response, but here, the response didn't even happen. The request never even happened. And if we look at the network tab, we can actually see this. So this is the request that actually got sent to localhost, but you'll notice it's not a put. What it actually is an options, because put is a pre-flighted request. So the browser didn't actually send put. It actually sent options first to ask for permission. And one thing that's kind of weird you might notice is the server is actually saying put's fine, which doesn't seem to actually match with the behavior we saw, because we saw that it didn't actually send the put. So what I think is happening here is that Express, for whatever reason, just defaults to allowing all methods. But it's OK. It's still getting denied in this situation because the response doesn't include a line that's explicitly allowing this origin. So basically, the attacker, what's going on here is this is a cross-origin request from attacker.com to localhost. And the response didn't say that that's OK. And so what ends up happening, if you look at the console, is you get the error that's saying access to fetch at localhost from origin attacker.com has been blocked by CORS policy. Response to pre-flight request doesn't pass access control check. There was no access control allow origin header. So this origin is not allowed because that header was missing. And so even though the server said, hey, puts are fine, the browser's still not happy because the server didn't say that this request can go through from this origin. And so anyway, the point is we were able to basically defend our local server by saying we're going to require this request to be a put in order to actually treat it, treat it as a real request and actually open up the dictionary. So it seems like we've prevented the attacker from being able to open up the dictionary at this point with this simple change. That was a lot to digest, I know. Any questions? Yeah?
The error is so that you can add something to the request to get around the...
Oh, it's actually wrong. This error message is wrong. It's saying set the request mode to no cores, blah, blah, blah. Yeah, that's a complicated feature of the fetch API, and this error message is actually incorrect. That often is a useful thing to know, but in this situation, it doesn't help you. The idea behind no cores, I'll just quickly say, is it's a way to sort of remember how I mentioned you can simple requests are fine. You can send simple requests to any place you want, and generally the way you do this is you put an image tag in the page or something like that. Well, for a long time there was no way from JavaScript to actually create a simple request because the assumption was if you're making this request in JavaScript, it's probably using some additional features that you couldn't use from HTML. And so those were just always blocked by default. This is a way where you can say, you sort of say, no, actually, I promise you, browser, that this is actually going to be a real simple request, even though I'm creating it in JavaScript. I'm not going to use any features that I'm not allowed to use. But that doesn't help us here because we're doing a put, and by definition, a put is not a simple request. So that wouldn't help us. Yeah.
So what's the appropriate response for the options request that would allow you to read the response?
Yeah, great question. So if we just send this header right here, along with the allow that this server's already sending. So if we did res.set that header to attacker.com 9999, like that. So that combined with the other header that Express is already sending should make it work. So if I refresh, we'll see if it works. Let's see what actually got set. It's not being sent. Oh, yeah, the problem is we have to actually support options. We don't even support, we have to do this. We have to add a completely new handler to say we want to handle options requests, right? And then in there we need to say, okay, we want to allow that origin and we want to allow puts like this. And then I actually haven't tested this, but presumably this would work. Let's see. Oh no. What happened? What kind of a request is this? It doesn't even see a method. Maybe I shouldn't do this live. Yeah, there's a way to do it. I'm not sure off the top of my head what the... Oh, it didn't actually send back a response. We need to do res.send. OK, something like that. So now we said put, and we said allow attacker. Oh, and sorry, that's not actually an origin. I need to add a protocol to it for it to actually be an origin. OK, this should work. No, it's not working. OK, what's the problem? Oh, see, access to fetch localhost from origin has been blocked by cores. Method put is not allowed by access control allow methods. Oh. Yeah, oh, OK, I don't know what this allow is then. OK, let's switch it to that. And then, there we go. OK, all right. So that's some live debugging for you there. But yeah, so basically, if I do that again and we look, the actual headers that are going on here are, so options gets sent to the server. The server says, put is allowed, and attacker.com 999 is allowed to go ahead and do this put, and then the browser follows up with an actual put right here, and then the dictionary is opened. OK, cool. All right, so, but again, this is still vulnerable to DNS rebinding, and we'll talk about that in a second. But first I wanted to mention, where is it? Yeah, so firewalls. So firewalls, enterprise firewalls, very common. Your house effectively has a firewall. When you have a router in your house, that's acting sort of as a firewall. Your OS has a firewall in it, and so let's talk just a little bit about those to understand like what additional power this type of attack gives us to get around firewalls. So normally, without any firewalls in place, your browser and the internet are sort of can freely communicate with each other. So you can make connections to the internet, and the internet can make connections to any servers running on your computer, right? So if you're listening for connections and some other computer on the internet wants to connect to that server, then that's going to be allowed. So we introduced firewall because the idea is this firewall can help us do the right thing in more situations. It can help protect us in cases where the local server on our computer is insecure by just outright blocking requests from even coming in. And so in the normal case, when your browser connects to the internet, the firewall sees, oh, this is a request coming from a browser on the network. And so because it's initiated from inside the network, the firewall says, yeah, let's go ahead and allow it. This is just the user probably visiting a website or doing something totally normal. But the reverse is not allowed by default. So if some random computer on the internet wants to connect to your IP address and they know the port of a server running on your computer, the firewall is going to see that and say, wait a minute, like this is not OK, and it's going to block it. And particularly just because it's an unsolicited communication. There was no indication that you were expecting this connection, and so it's just going to block it. So this is really great because there's all kinds of devices on your network that are very, very insecure. The IoT devices that I mentioned earlier. There's all kinds of things now that have like computers inside them, like refrigerators and TVs and printers and internet-connected webcams. And a lot of this software was written with an assumption that other devices on the same network may want to communicate with that device. In particular, think of like a Chromecast, right, or an Apple TV that's on your network. It's very common, it's expected that other devices that are on the same Wi-Fi network would be able to make connections to that Apple TV directly. But a lot of these devices assume that the other devices that are allowed on your Wi-Fi are devices that you yourself own or devices that you trust, or else you wouldn't allow them onto your Wi-Fi, right? And so the fact that random computers on the internet aren't allowed to make connections to these devices is really, really good, because oftentimes the devices just assume that anyone who can make connections to them is trusted, which is definitely not true, right? If you're getting a connection from the random, the public internet from a random person. And so this is really great that the firewall does this for us. And so like this would be really bad if anyone on the internet could send packets to your printer. Bad things would happen. They'd be able to create print jobs. If there were any vulnerabilities in the printer, in the server that's listening in the printer, then the attacker would be able to try to attempt to exploit those by maybe there's some kind of an injection, a command injection or something on the printer, and an attacker would be able to attempt to exploit that. The other thing that makes this really pernicious is that these devices often never get updates. These IoT devices are like sort of fixed at factory time when they're produced, and then people rarely, if ever, apply updates to their printers or to their refrigerators. Or I recently saw a tweet from somebody who literally, when they just got a new toilet, and the first thing it told them was they needed to apply a firmware update to it before they could use it. And but yeah, like at least it notified them that the toilet needed an update. A lot of these devices don't tell you that there's updates available, and there's no way to know. And so you'll just have a vulnerable device on your network for a really long time. But yeah, isn't it a wonderful world that we live in now with all these internet-connected devices everywhere? But yeah, so anyway, yeah, if anyone could just send packets to your printer or to any of the devices on your network, they'd probably be very quickly owned. And then from there, once you own a printer, like it's not that useful to be able to print pages out on some random person's printer, but you can use that as sort of a point from which to pivot and to traverse horizontally through someone's network, because now you're basically, your attack code is running as a device that's on the network, and it can communicate with all the other devices, and so you can sort of quickly infect a bunch of devices that way. And so yeah, so the fact that we have everything going through this firewall, either in our router or our enterprise firewall or something like that, is really good. And I mentioned that your OS has a firewall built into it, and if you've ever seen any of these before, that's the Mac OS firewall settings, and this is like an alert that pops up frequently on Windows. This is sort of the OS firewall in action, and I'll mention a little bit more about how those work later, But yeah, so basically, so what do we mean when we say we can use the browser as a proxy? What is going on here? Well, what's going on is that if you have a firewall in place and the internet, people on the internet can't talk to any of your devices, there's still a way that they can talk to the devices, and that's by using your browser as a proxy. So what they do is, you go and visit a website, right? So you make a request. The firewall sees that you made a request to some website. And then that site responds, and the firewall allows that response through because it knows that that's the response to the request that you sent, and obviously you would be really upset if you couldn't view the website you just visited, so that's allowed. The website loads in your browser, and then JavaScript running in that attacker's website makes a request to a local IP address, like 192.168.1.100, which is a local IP, which is the IP address of your printer, let's say. And of course, again, like I said, the printer and all these IoT devices often assume that these types of requests can't be sent except by devices that are on the same network. And so the fact that like random JavaScript code running in an ad can make a request to your insecure IoT devices is quite concerning. Now, we have a few things that can protect us here, hopefully. We already know the same origin policy applies. So an attacker, they can't send a non-simple request to your printer, hopefully, right? And so they can only they have to suffice with GET requests and and posts, form posts basically. But they would be allowed to send those to your printer, which is still kind of concerning because I don't know how secure that code is, right? But yeah, if they can send a request that manages to infect your printer, then you're back into the situation where you now have an infected device on your network that can do who knows what, right? If it's a camera, it can watch you and send video frames off to some attacker. If it's a toaster or something, it can launch attacks against enemy states or whatever. Like there's all kinds of stuff that these IoT devices are doing. It's seriously true. Yeah. So okay. So. And then, of course, like this is not just about IoT devices, it's also about local servers. So the same thing applies to any local servers that are running on your computer. So if you are, again, you're browsing the internet, you make a request to a site, you get back a response. The code on that site can make requests to any local IP addresses that it wants. And if it knows, like, hey, this is your local IP address, or if it just uses localhost, then in some port, it can just guess, like, oh, you're probably running your development server on port 4000 or whatever. Or it can iterate through a bunch of ports. Then it can make requests to these local servers on your computer. And if they're vulnerable, then you have sort of the same issue as before. And this is basically the Zoom attack. This is just another way of representing the Zoom attack that we've already talked about. Okay, so yeah, we tried to defend against this by making all the sort of sensitive functionality in our Zoom server. We tried to make it require a put request. And we were hoping that would make it harder for code running in an attacker's page to be able to actually send that request, because it requires a preflight and all the things we just talked about. And so we're thinking, okay, now there's nothing that can happen. But of course, now we're going to talk about how to actually do DNS rebinding, because this is still, we haven't fixed DNS rebinding yet. So let's go ahead and look at the code again. And let's see here. So what I want to do is I'm going to change up the code in this page a little bit. And so instead of immediately calling fetch, what I'm going to do is I'm going to make a button on the page. And I'm going to call it, I'm going to make the text in it say send a put to. And so this is the attacker. The attacker site is going to have a button that says send a put to. And you would think I would want to send the put to the local server, localhost. But actually, the way this attack works is I send the request to attacker.com. And instead of 999, I'm going to make it 8080, which is the same port as the local server. OK, so hang with me for a little bit. This will all make sense in a second. And so that's what this button is going to do. So now what I'm going to do is I'm going to have code that doesn't run this until I click the button. So I'm going to say document.querySelector. I'm going to select the button, and I'm going to say button, and I'm going to say when the button is clicked. So add. Let me make this bigger for you so you can see it. Sorry about this. OK, add event listener. What I'm going to do when the button is clicked is I'm going to run this fetch code like I was going to do before. But the only difference now is instead of making the request go to localhost 8080, it's going to go to attacker.com 8080 with a put. OK, so this doesn't seem like we're attacking the local server anymore. We're just sending a put to ourselves as the attacker, which isn't going to do anything. It's not going to pop open the dictionary, right? But we'll see. There's one more step we need to do here to actually pull this off. And so, first step 2, I should probably, on the local server, I should delete the extra option stuff we added from before. So we go back to our supposedly secure state before. And so now let me see what happens. So if I load up, let's see here. What I want to do is I'm going to move this code quickly to an actual remote server. Where is that? Did I do that? Did I not do that? Oh, you're right. Thank you for that. Yep, add event listener click. That's the code I want to run. OK. Now what I'm going to do is I'm actually going to put this on a real internet server because I can't have 2 servers running on the same port. And so I actually need this to be on an actual separate computer. And again, the port should be 8080 there. OK. All right. So now if I save this and I run the server, OK, so now I have this code is running on a real server. And then what I've done here in my etc hosts file, this is a way where I can sort of override my DNS settings. So normally when you connect to a site, the first thing the browser does is it says, what is the IP address for this host name? And it asks the DNS server and gets back an IP address. And what I want to do here is I'm not going to go and buy a domain for this demo. So what I've done is I've hard-coded here that I want anytime before the browser actually does the true DNS request, it's going to look in this file, and this file is going to take precedence over the true DNS response. And so what I've said is I want attacker.com to map to the IP address of that server that I just put the code onto. Okay, so this is basically simulating what would happen if an attacker just bought a domain, pointed the domain, made a DNS entry to point the domain to their server. This is like very standard, the way that you deploy a website. Nothing magical going on here. All I'm doing is I didn't want to actually buy a domain, so I'm locally hard coding that in. Does that make sense? OK, so now when I go to attacker.com 8080, that request is going to actually go to this server, and that code that we wrote here should actually run. And let's see what happens. OK, so I'm going to refresh this. Oh yeah, and here's how you can tell that it works. Before I refresh, notice when I visited attacker.com 999 before that it says the remote address that it actually sent the request to was my own computer. Now when I refresh, it's going to actually be nothing. OK, great. Oh no, I need to change it to 8080, right? OK, no, it still doesn't work. Oh, thank you. I'm so glad you're here, John. You keep catching all the mistakes. OK, all right. Now I need to update the code on the server. Give me a second. Sorry, this is actually, there's no simpler way to demo this. It's actually a very super complicated attack to demo. So apologies in advance. There we go. OK, so now I visited this attacker.com 8080, and the code that we just wrote is running now. And you'll notice that it actually connected to a remote server to load this page. OK. OK, now if I click this button, then nothing interesting is going to happen. We just sent a put to ourselves. And this is this server that we wrote, and this server literally doesn't do anything in response to a put. Like you can see here, all we've implemented is a get on the attacker's end. So this is useless, right? But here's where the cleverness comes in. OK, so what I'm going to do is I'm going to so this is the attacker site's loaded, and what's going to happen now is when the attacker sees that we've landed on their attack page, they're going to have code in the background that goes and changes their DNS entry. And instead of it pointing to the true server where their code is running, they're going to point it to a localhost IP address. OK, so check this out. Here's how we're going to simulate this. I'm going to go to the etc hosts file, and I'm going to say, all right, instead of pointing to 116, we're going to comment that line out, and I'm going to replace it with that line. And so now, notice, we're still on this page. We're still on the attacker's page. But the attacker has basically updated their DNS, which is, and anyone who controls a domain can do this. You're basically just saying, my server is no longer at that IP. It's actually at this IP. But the weird thing is this is actually localhost. This is not a real IP that the attacker's server is actually at. But they're allowed to do this. They're allowed to say, they basically are telling the browser now, hey, whenever you make requests to attacker.com and you look up the DNS, I'm going to give you localhost, and then you're actually going to connect to localhost when you send that HTTP request. And so this request now is going to go to the local server that opens the dictionary on our computer. And so now when I click this button, the dictionary opens again. And so, oh my gosh, even though we made it a put, the attacker was still able to send a put. And they sent this across origins. It seems like they violated the same origin policy, because they literally sent this. This is code running on attacker.com. They sent JavaScript to us, and then it made a request to a server on our computer, which is a completely different origin, right? But that's actually not true. So what's going on here is, from the browser's perspective, we are on attacker.com, 8080, and we just made a request to HTTP attacker.com 8080. So that's the same origin request. It's allowed, right? We can send whatever kind of request we want to ourselves. As far as the same origin policy is concerned, this is a same origin request, because the three parts that make up an origin are exactly the same in the request as they are on the page that we're on. And so this is a same origin request. It's totally fine. But the key I guess problem here, if I could point it out, is you'll notice that the put that we sent that went to the local server, it's connecting to 127.0.0.1, but the initial page was loaded from a completely different server, 50.116.111.184. And that sort of DNS change happened in the background. And the same origin policy has no conception of IP address. It doesn't care about the IP address. That's not part of the same origin policy. It's not relevant in determining whether two things are the same origin or not. So yeah, that's DNS rebinding. Any questions? Yeah?
So how is attacker.com able to know what port the local server is running on, given an arbitrary, if an arbitrary website visits attacker.com, will they be able to pool the port at all? Because if they're connected to a different port, they won't be able to execute the attack, right?
Yeah. So the way this would work in practice is the attacker would probably have a particular device in mind that they want to attack, and that device would have a particular port that it uses, and they would know to make their server just use that same port. But even if they didn't want to do that, they could also just try all the ports, because there's not that many ports. There's only 65,000 ports. And if you've ever kept a tab open in your browser for a week, like I have, that tab could just be trying all the ports. That's plenty of time to try all the ports and find the one that your application happens to be using, because 65,000 is just not a very big number for computer. Yeah.
So when we change the routing in etc hosts, is that actually how DNS rebinding is done, or is that kind of just a fill-in for what an attacker would do? Is that actually how?
No, that's a great question. That's a fill-in for what the attacker would do. So the way that you would experience this as a person who's getting attacked is that you would just visit attacker.com, and as soon as you visit that initial page, the attacker knows that you just visited it, and so they're going to go now and swap the DNS, and they're going to make it point to 127.0.1, which is localhost, and then also, they're not going to have you click a button to own yourself. That's just going to be like a thing that they just keep continually pull in the background. Like every 10 seconds, they'll try sending a put to that address. And the reason why they need to try multiple times in the real world is because the browser may be caching the DNS response. And so say it's cached for like a minute or something like that, then the first time they send that put, it's going to be going to the attacker's actual server instead of the local server they're trying to attack. And so they have to actually just keep trying until the cache entry expires. But the good news is, well, good news for the attacker is that you can set that to be really short. You can say basically, don't cache this for very long. Like you can put it in the order of seconds, and so it, in practice, the cache isn't really an issue. But yeah, the way you would experience this as a person getting owned is you would just visit the site, and you'd be on it for like 10 seconds, and then this request would get sent to the server on your computer or your vulnerable IoT device, and that's it. You didn't even experience anything. It's sort of an invisible automatic attack. It just happens.
So I guess like how does the attacker actually have access to change like the DNS binding on your device?
So that's a great question. So they're not actually changing this DNS binding in this Etsy host file on your own computer.
Like where is that happening?
Oh, where's that happening? Yeah, so when the attacker registers their domain name, they actually specify, they tell the company they registered the domain with, this is the server I want you to use whenever whenever anybody asks, does a DNS lookup, basically, whenever a DNS query comes in. And so they basically point it to some DNS server that they have control over as an attacker. And so because they have control over it, they can just change the IP that gets returned in the answers anytime they want. They can literally just, they can change it on the order of every second. Like they can just keep swapping back and forth between the attack IP and then the localhost IP and just do that as much as they need to. Yeah. The only sort of unpredictable part of this is like they don't know for sure how long the entries are going to be cached by your browser, but like it's relatively short. Yeah. Mm-hmm.
Is there a way as a client to say like don't parallelize my requests if possible and just like use one TCP session? Because wouldn't that prevent this?
That's a good question. So you're referring to this thing called Keep Alive. So the browser has an optimization when you're repeatedly talking to the same server. One thing that it might do is it might just keep the TCP connection open and send multiple HTTP requests over the same connection. And if it decides to do that, then we're in trouble because we actually want it to disconnect, and we want it to do a new DNS lookup to get the new IP address, and we want it to create a new TCP socket to the new IP address in order for the attack to work. And so, fortunately, since the attack, again, I keep saying fortunately because I'm thinking from the perspective of an attacker, but yeah, fortunately for the attacker, they have a way around that, which is they can just include a header, and I don't know if it's included here. Okay, no, yeah, so the wrong header is being included right now. The attacker is including connection keep alive, which is actually specifically asking the browser to keep the TCP socket open. I think the reason why it's not listening is because I'm in disable cache mode, and it's probably not using that, or maybe we were on the page too long or something, but you can change this to say close, and then the browser will just close it every time, and then this makes the attack more likely to work. Yeah, you just say connection close to opt out of keep alive. Yeah? That is a good question. I guess there's some legitimate use cases for it sometimes. I don't know.
Would that fix this attack?
Yeah, I mean, well, okay, I don't think the correct place to fix this wouldn't be like in the DNS software itself, because the attacker can always like modify their DNS software to return, whatever IP they want. But you could imagine the DNS resolver running on your laptop, or the DNS resolver running that your ISP is running for you. They could refuse to accept responses that point to localhost if they wanted to, and that would completely kill this attack. Yeah. In fact, I think some enterprises actually just do that because they know they're running a bunch of vulnerable printers and other kinds of random garbage devices on their network that they are worried about, and they don't want they don't want random website JavaScript to be able to try to attack it. So yeah, that would fix the problem. I don't know why. I don't know. John, do you know? My friend John is here, by the way, today. So he's the one who kept pointing out my mistakes. He might know the answer to this.
I don't offhand.
Okay.
I mean, just denying localhost wouldn't fix the problem because then you could still point it at your printer. I mean, ideally, to fix it, you'd have to block everything on the local network.
Oh, that's a good point. Yeah, the other thing. It's not enough to just block like 127.0.1 because there's a whole entire range of IP addresses which are mapped to the local devices on your network. Like you get given a 192.168.0.1, some kind of IP like that starts with 192.168, and those are all local device IPs. So they could also just iterate through those. So you have to block all those too. Yeah, I don't know. It's the one before I hear your question, I just want to also mention one, I guess, kind of legitimate case where I've seen this used is there's a yeah, and I don't even know why they needed to do this, but there's a server, a local server built into Spotify when you have the Spotify app on your computer, and it's similar to Zoom. You know, it's again another one of those things where it's like, why are they doing this? Why are they running a local server on my computer just to play? You know, it's a music player, like it doesn't need this functionality. But yeah, there's a local server on your computer, and it's listening on like some port, some high-numbered port, and they bought a domain called spottylocal.com. And if you do a DNS lookup on that, we can just do it right now here. You'll see that spotty local. Let's see here. Why is it? It says A, but then it doesn't. Let me just go to a DNS lookup website. We can see it's pointing to localhost, I believe. Not found. Maybe they don't do it anymore. Anyway, well, at one point, Spotify used to run a local server on your computer, and then they had this domain that they registered called spottylocal.com, and they would use that. They would basically they would send requests to that, and those requests would control the Spotify player. But in order for the requests to actually get directed to the local server, they did the same DNS trick where they mapped it to the local host IP. And I don't know why they didn't just hard code like 127.0.1 or whatever, but that's what they did. Maybe there's a reason. There may be a reason.
Just want to point out, if the DNS server of the attacker is different from your own DNS server, there will be some time for the change for the DNS record to propagate to your own DNS server. So they have to do this in a longer period of time.
Yeah, that's a good point. Yeah, so what you're referring to is like, because DNS is like this hierarchical thing, it may be that the attacker updates their DNS on the server that they control, but then when you actually go to look it up, that goes through your ISP's DNS server, and eventually, the request goes to the real server, but your ISP server may cache it for some period of time that is like longer than what the attacker requested. But if the attacker says like don't cache this for more than a few seconds, then you would hope that the ISP, as an attacker, you would hope that the ISP would obey that and not actually cache it. But I have heard of DNS servers that actually have like a cap on, like they won't actually obey like a 1 second cache time. They'll still cache it for like 10 minutes anyway. And if they were doing that, then this attack would take 10 minutes to succeed. So yeah, it's possible that it doesn't work all the time. Totally, yeah. Yeah.
I think you're just reading some more policy stuff, but is there a reason the attacker couldn't just like register 256 subdomains for all the possible, for different destinations on your local network? Like that would no longer be same origin.
Yeah, exactly. Because same origin is protocol, hostname, and port. I mean, it is actually kind of an interesting point. Like an IP address isn't really a host name, but the browser kind of treats it like a host name for purposes of same origin policy. So every different IP is a different would cause a different origin to be created. Cool. Any other question?
Can I bind attacker.com to some bank website and then read your credit card number?
Okay. Yes, I was gonna ask this at the end. I'm so glad you mentioned it. Yes. So this attack seems like if you can break the same origin policy in this situation, isn't it really bad? Can't I now like basically use this trick to like instead of updating my IP to be 127.0.1, I update it to be the bank's server's IP, and now I can send requests to it? Yeah, that's totally doable. But why is the damage limited in this situation? It's actually not really a big deal. It's much less of a big deal than it is in the local server case. Can anyone think of like the difference between those two scenarios? It's kind of subtle. Okay, so let's like mentally walk through like what you're suggesting. So you're suggesting I visit attacker.com, and once I've done that, the attacker goes and updates their DNS, but instead of updating it to 127, where is it? Right here. Instead of updating it to 127, they update this to the bank's IP. They change it to, you know, whatever that the bank is, 4.4.4, something like that. Okay, and then when this button is clicked, or when they cause the next request to get sent, you know, this is now going to go to the bank, right? Question for you: when this request goes to the bank, it's going to the bank's IP, right? But from the browser's perspective, what origin are we on? We're on this origin, right? http://attacker.com, whatever the port happens to be, right? Yeah, that's exactly right. So the bank is gonna there's many things the bank could do, but one of the things the bank could do is what you suggested. So it will say, oh, a client has shown up. Let's do a TLS handshake. Blah blah blah. We're gonna have an encrypted connection, and the certificate that it sends is gonna be for bankofamerica.com. And then your browser is gonna say, what is this? I'm talking to attacker.com. Why am I getting back the certificate for bankofamerica.com? I'm being man-in-the-middled, you know, and it's gonna block this. And so that will cause a an HTTPS error. Another issue, say you're attacking a site that's not HTTPS. So now you don't have that problem. There's still another way, there's another reason why this is not a big deal, I'm arguing. Yeah? The cookies, yes. Again, the browser thinks you're talking to attacker.com. So it's not going to send the cookies for the bank. Even though you did trick the browser to connect to the bank, it thinks it's talking to attacker.com. So it's going to helpfully attach attacker.com's cookies. And so you won't actually be authenticated as yourself. And so all the requests you're sending to the bank won't do anything. And so, you know, it's not really a big deal. You have to remember, from the bank's perspective, anyone can send them a put request by writing a Python script or a Node script on their computer. And so it's not a big deal if you can just make someone's computer like send a put to the bank. Like the attacker could have done that themselves. The real power of the attack would be if there was a way the attacker could cause the user's cookies to get attached. So you get that ambient authority that we talked about, where you can take actions on behalf of the user. Yeah. Okay. Yeah.
And that wouldn't necessarily happen because of things like same site, for example, or CSRF tokens.
Exactly. That would prevent it as well. Yep. Exactly. Yeah. So yeah, it's much less of a big deal. But so the reason why it's a big deal with local servers is because the local server usually is making an assumption that anyone who can send requests to that local server must be on the same network as you and therefore trusted. Think about how your printer operates. Anyone who can send packets to the printer can print. It doesn't ask you to authenticate yourself. It just prints, right? Well, maybe not at Stanford, but in general, that's the way printers work. And so yeah, it's the same thing. It's the same idea here. So the local server is making this assumption that is inaccurate. OK, so we are almost out of time, so let me wrap up here. So yeah, this is a visual version. This is a visual of like sort of what is going on in this attack. If what we've talked about so far doesn't make sense, hopefully this makes it clearer. So this is every step involved in pulling off a DNS rebinding attack. So we have a browser. We have a local server that we want to attack. We have a DNS server that is controlled by the attacker. What do? Well, the attacker gets us to visit attacker.com. First thing our browser does is it does a DNS lookup to figure out what the IP address is for attacker.com. Say it's 999. Now, the browser is actually going to make a TCP connection to that server and then send the HTTP request over it. And then we get back the attacker's website. So far, everything's normal. The attacker's site loads. Now the attacker's site is going to include a JavaScript code in it that causes a fetch to happen. And this fetch is going to be back to the attacker's origin. So the browser is going to see this request and say, hey, this is the same origin request, right? So let me just go ahead and allow it. I don't need to do any kinds of checks because it's the same origin request. So it goes ahead and now here we're relying on the fact that enough time has passed that the DNS response, that 999 answer, has expired. And so the browser actually doesn't have it cached, and it has to ask again. It has to ask the server again for the IP address. And so this time when the DNS server gets that query, it doesn't respond with 999, it responds with the local IP instead. And so now, when the browser actually goes to do the put, instead of it going to the 999 server, it goes to the local server instead. And one other thing is the browser is going to go ahead and ask a question, because remember, this, actually, wait a minute. Let's see. Yeah, exactly. It's the same origin. So it's going to say this is a request initiated by the code on attacker.com, and the request is going to attacker.com, and so there's no need to do a preflight or anything like that. It's the same origin request, and so it allows it to sort of just go right on through to the local server there, and then we go ahead and interpret it. And then in the case of the dictionary, it would open up the dictionary. In the case of Zoom, it would pop open the chat application, and we're vulnerable. So let's talk about how to prevent it in the last 5 minutes we have. So how can the server protect itself, and how could browsers potentially do something to protect both servers that are vulnerable or unaware of this attack and the users who've bought these cheap IoT devices that are insecure and there's really no way to update them at this point. So let's think about that. So I guess I was gonna open it up to questions, but we don't have time. So we'll just go on straight on ahead, and I'll show you the way to basically defend against this. It's really quite straightforward if you know about DNS rebinding attacks. The first step is to understand the attack, which it takes a whole class to explain. But once you understand it, the fix is one line. So this is how you fix it. You basically need to, in your server, check a particular header. Actually, let me just ask, does anyone know what header we might be able to check? Okay. The host header, yes. So the host header, what does that do? That tells the server what site the request is intended for. So if I go and open up the browser and we look, so remember that the browser thinks that we're trying to talk to attacker.com, right? And so what it's going to say is it's going to include this host header here that says, hey, this request is intended for attacker.com. And if you remember, I mentioned one of the reasons why this header is really useful in general is because it's possible that a single server might be serving multiple different websites. So if a server is serving site A and site B, and it gets a request from somebody, and if this header was omitted, then there would be no way for the server to know what site the request is intended for, because you'll notice that no other part of the request actually includes this is misleading. It's showing it's the URL up here, but if you remember the format of HTTP requests, they're formatted get space slash space whatever HTTP, and that slash is just the path. It doesn't actually tell you the site. And so this host header helps the server to figure out what actual site are we supposed to serve here. And so what if we just looked at that host header, and if we see that it's not localhost, but actually it's coming from attacker or any other origin, then we know that this is not normal. This is a DNS rebinding attack. So that's all we're going to do here. I could put the code right here, directly in the put handler, but then I would need to remember to put this code in every single handler that I add in my server. And so instead of putting it here and having to copy paste it throughout all the other handlers I might add in the future, what I'm going to do is I'm going to add a middleware. It's called a middleware. And I mentioned this a little bit before, but basically what this middleware is going to do is it's going to run first before any of these other handlers that I may add in the future that look like this. And this is always going to run first because it's in the code literally first. I'm calling this function before I'm calling this one. And so that function is going to run first. And what that function is going to do is it's going to check if the request's host header is not exactly equal to local host, what's the port is on again? 8080. I think that's host, right? Or I can't remember if the port is included or not. Let's include it and see. So if the the host header is not that, then I'm going to throw an error, DNS rebinding attack. Otherwise, I will call next. What next does is it says, basically, just move along to the next potential handler that might match this request. And so just like that with a couple lines of code, now if I go and I go ahead and try the attack again, it shouldn't work. Let's check that out. OK, so what I'm going to do is I'm going to set it back to the public IP address. I'm going to refresh. And now we'll just confirm it made the request to the public server that's on the internet. And then now the DNS is going to get swapped to the local IP. This is the attacker doing this. And then now, if I click this button, the request got sent. But what you'll notice is that the server, that code ran in the server that we wrote before right here, and it actually refused to process the request because it noticed that the host was attacker.com instead of localhost 8080. And so it's like, okay, this is not a valid host header. I know that this must be code running on attacker, and they've done this sort of DNS rebinding trick to try and trick the server. Yep. So, oh man, next time. So yeah, that's DNS rebinding. It took a whole class to explain. It's really complicated. You should pat yourselves on the back for understanding it now. If you ever in your careers write a local server, be very, very careful. Don't do it. Argue really hard not to do it. If you must do it, then go back and look at these slides and be very afraid about doing it, because you're probably going to get it wrong. I got it wrong. Everyone gets it wrong. So be very careful. Thank you. See you next time.